For example 8, if f is a continuous function on the closed interval from 1 to 5, with f of 1 being negative 8 and f of 5 being 3, then must there be a value of c in the open interval from 1 to 5 such that f of c is equal to e? All right, so this question is very similar to something that you might see on a calculus exam, on the AP calculus exam. Now, it's probably not necessarily a yes or no question. They'll probably ask it in a, I guess, more elegant fashion to allow for some answer choices there. However, how do I even know that this is supposed to be an instance of me applying the intermediate value theorem? All right, so there are some clues here. So what we're trying to show is just about existence. Then must there be a value of c in this open interval? And notice the conclusion here. So I'm recognizing this conclusion as being something that fits the description of the intermediate value theorem. It also points out that you have a continuous function on some sort of closed interval, and it gives you some endpoints. So I need a familiarity with the intermediate value theorem to be able to pick it out of a particular question and understand that that's what it's asking me to do. Notice that in no kind of way does it use the words intermediate value theorem. All right, so we just have to make that association when we want to have that thing committed to memory or, tattooed on a place in our body that we can easily access whenever we're taking the AP exam. All right, so let's see how we should write up the solution to this thing. This one calls for a blue crayon. All right, so remember, if I'm going to apply the intermediate value theorem, I need to make sure that I satisfy the conditions. And the conditions, the first one is continuity on a closed interval. And we have that, right? But I need to point it out. Since f is continuous, pretend like this is in italics, right? So this needs to be like slanty like that. Maybe I can try to do that here. Let me try. Whoop. Wow, that's super fancy. Okay, if f is continuous, since f is continuous on this closed interval from 1 to 5. All right, so the first one is checked off. We've done it, right? So look at my checklist. Check. Now I need to establish my inequality. So what do we need? We need e. E is about 2.71728 something, blah, 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 right? Okay, so I know it's between 2 and 3. And this is good because look at my two y values here, right? So I just want to set up an inequality. This number here, e, is definitely in between -8 and +3. So I'm going to set up an inequality like this. So, and let's say f of 1, which is equal to -8, which is less than e, which is less than, well, what's the other number? 3, which is the f of 5. There it goes. I have just established my inequality right here. So there's the second one there. I am free to make my conclusion right here. Bam. Since f is continuous on the closed interval from 1 to 5, and f of 1, which is equal to -8, which is less than e, which is less than 3, which is equal to f of 5, then there must exist a value, that says value, by the way. If you don't believe me, let me rewrite it for you, of c in the open interval from 1 to 5. Or you can write this thing as an inequality like this. 1 is less than c, which is less than 5, of course, such that f of c is equal to e. Bam. Now, one extra little bit that you could put on here if you want to is by the IVT. But from what I understand about the actual AP test grading process, you have satisfied the conditions, so this part is just kind of understood. As long as you draw the proper conclusion, by the IVT is a little extra. All right, let's look at our final example here. Something a little bit more algebraic. Example 9. use the intermediate value theorem to show that the polynomial function f of x is equal to x cubed plus 2x minus 1 has a 0 in the interval from 1. No, let me try that again. From 0 to 1. Okay. Now notice it doesn't tell me to actually find it. Now this one is, a little bit contrived because it actually tells you to use the intermediate value theorem. But if I'm going to use a theorem, I need to make sure that it satisfies the conditions. Even though it says, hey, use it, well, I can only use it if I'm allowed to use it. Well, can I use it on a polynomial function? Yeah, I can. And the reason why is that no matter what, every single polynomial function is continuous everywhere. So that is the first thing that I am going to make sure that I point out. But, more than that, if I come back up to my my checklist, I also have to be able to do this. I have to guarantee that I have a 0 in between my two y values. And I haven't even examined what those are. So I could pretty easily do this, right? I could do this probably by synthetic division. I'm going to plug a 0 into the function. Boop, boop. I'm going to plug a 1 into the function, and hopefully my y values change from, say, a positive to a negative or negative to a positive, right? Okay, so let's see. Actually plugging in 0, I'll just do that by direct substitution. That should be pretty easy. I get a 0 cubed plus 2 times 0. I may need my calculator for this. It looks like it's -1. All right, maybe I don't do synthetic division for the other one either, because it's just 1 I'm plugging in here. So 1 cubed plus 2 times 1 minus 1. These two 1s cancel and I get 2. Well, look at that. We have a sign change, right? So if you wanted to kind of think of a graph here, that at 0, what color should we choose? Okay, blue. At 0, we're at -1 for the y value. So it's, it's like right down here. And then over at 1, we're at +2, and let's say that it's right about there. So in between those 2 points, well, yeah, obviously I've got to hit 0 in between there. Right? And it's because, boop, this thing is continuous. Make sure we point it out. Well, how do I know that polynomial functions are continuous? Well, if you will recall, we had a theorem someplace around here. It's right here. Bam! The following types of functions are continuous at every number in their domain. And it was right there. It's polynomial. I just have to state it. That's it. I just have to state it. I make sure I point it out. And then I'll be covered. Okay, so this is how I might state it. It looks like we're going to stick with purple. I hope you guys don't mind. Okay. Maybe I say something like, since f of x is a polynomial, it is continuous everywhere, right? That just simply means from -infinity to +infinity. So it must be continuous on the closed interval from 0 to 1. Let's go back to my checklist. Now I'm going to put purple checks on there. Check. Now I need to establish my inequality. Let's see. How about I, really make this sound juicy with some repetitive English here. So since, let's see, the inequality would be, we're going from -1 to +1. All right, so since f of 0, which is equal to -1, which is less than 0, which is less than, the other one was 2, which is the other endpoint, f of +1. I believe I did that correctly. All right, there we go. So we have satisfied the other one. Let's put another purple check mark on that guy. Boom. And now let's satisfy the conclusion. Since blah, 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 then there must exist a value of c in, let's see, this open interval, right? Open interval from 0 to 1, such that f of c is equal to 0. Boom. By the intermediate value theorem. Which brings us, ladies and gentlemen, to the end of this lesson here on continuity. We were able to apply the conditions of continuity, of which there were 3. Your point has to exist, the limit has to exist at that point, and the value of the point and the value of the limit have to be the same. Oh, and speaking of continuity, that is a major condition of the intermediate value theorem, which basically states when you have a continuous function over some sort of closed interval with the endpoints not being the same, your function takes on every single value in between those 2 endpoints. Awesome? Okay, we're done.